Hi, everyone. We'll be getting started in just 1 minute. We're just allowing folks to trickle in here. Hello, welcome everyone, and thank you for joining us today for NOAA's Climate and Societal Interactions Nature-Based Solutions webinar series. This is the 5th episode, titled Challenges and Opportunities of Scaling Nature-Based Solutions for Climate Adaptation. I'm thrilled to see so many people joining us today. My name is Jeannie Bay, and I am a program specialist supporting the Climate Adaptation Partnerships program at NOAA. Next slide, please. Before we begin, some quick housekeeping notes. If you can hear me and see the presentation, you are good to go. We are excited to have live Spanish interpretation available for today's webinar. To enable hearing Spanish audio, you can click on the headphones icon and select Spanish. And to go back to hearing the English audio, you will need to select None. Unfortunately, we are not able to support folks in troubleshooting technical issues. We recommend rejoining the session if you are having trouble connecting. For the Q&A session, which will occur at the end of the webinar, you can submit questions to the speakers using the question function. And finally, this webinar is being recorded, and the recording will be sent to all registrants and posted on our website at a later date. Next slide, please. So we'll begin by providing some brief overviews of the webinar series and the NOAA programs that fund the featured work. And the bulk of the time today will be dedicated to our presenter, who will be sharing insights from his funded projects. And then we'll have about 10 minutes or maybe a bit longer for questions and answers at the end. Next slide. This webinar series features projects funded by the Climate and Societal Interactions Division, or CSI, focused on the research and equitable application of nature-based solutions, which are actions to protect, sustainably manage, or restore natural or modified ecosystems to address societal challenges, simultaneously providing benefits for people and the environment. Each webinar episode will feature different projects to demonstrate the diverse contributions that the CSI division has made to the body of nature-based solutions research and practice of implementation. Each webinar has a different focus, so we hope you'll continue to join us each month. And with that, let's shift to learning more about NOAA, CSI, and the Climate Adaptation Partnerships Program. Next slide, please. So I wanted to start us off by providing some situational awareness of where our division sits within NOAA. NOAA is within the Department of Commerce, and the NOAA Climate Program Office, or CPO, is hosted under the Oceanic and Atmospheric Research Line Office, or OAR. Next slide. The Climate and Societal Interactions Division within CPO supports research that seeks to generate the knowledge, tools, and institutional networks that enhance society's capacity to anticipate, plan for, and adapt to climate impacts. Our focus complements the work of the physical science research and development portfolio across NOAA by using insights from social science research to interpret, synthesize, and apply climate data analysis and observations. Programmatically, this is what CSI looks like today. It is a science policy research and engagement enterprise that brings to NOAA an emphasis on individuals and communities and the ongoing decisions involved in the process of adapting to climate, both here and abroad. CSI is home to 2 unique programs, the Climate Adaptation Partnerships, or CAP program, and the Adaptation Sciences program. Next slide, please. The mission of the CAP program is to advance equitable adaptation through sustained regional research and community engagement. We accomplish this by supporting a network of regional teams competitively awarded 5-year cooperative agreements through competitively awarded 5-year cooperative agreements in multi-state regions across the US. Teams are composed of experts and local partners working across a diverse range of sectors and with urban and rural communities and local, state, and tribal governments on their cross-sectoral climate adaptation needs. In recent years, the network has begun focusing more directly on equity and as well as tackling the complex compound stressors, both climate and socioeconomic, faced by communities, and has focused more attention on partnering with frontline communities. On the right of this slide is our ring graphic, which depicts the CAP process. And it is within these actions and outcomes that novel climate solutions are developed. The CAP program represents long-term investment toward this mission, as the program is over 25 years old, and our vision is to continue investing in existing regions and expanding into areas that are not yet covered by the program for the long haul. Next slide. Here is a map of our current CAP network and regional teams. The 13 CAP teams that make up the network are depicted in solid colors. These teams have been working in their regions, some over many years, to build relationships and produce collaborative research and community-relevant adaptation approaches. We are working hard to reach full national coverage, but that is largely dependent on congressional appropriations. Today, you will hear overviews of projects presented by a member of our Urban Northeast team. Next slide. CAP teams determine the research they engage in alongside the communities that they serve, taking into account the unique environmental, socioeconomic, and cultural variables of their regions. CAP approaches nature-based solutions work by applying this programmatic level lens of integrating social and physical sciences and considering complex compound hazards and benefits. This holistic lens allows for challenging more conventional approaches to nature-based solutions that may be solely focused on engineering and design, and rather emphasizes the importance of considering societal and community-level variables. Significantly, CAP's work spans both coastal and inland communities, making our investments in nature-based solutions distinct from many other NBS-focused programs at NOAA that are concentrated in coastal zones. NBS work funded through CAP can be loosely categorized into these buckets here, which include informing decision support and community planning, identifying trade-offs and co-benefits, advancing equity and workforce development, as well as analysis and evaluation of projects once implemented. More specifically, CAP has funded work on developing community-wide green infrastructure master plans, examining the intersection of extreme heat, human health, and nature-based solutions, conducting vulnerability assessments for stormwater managers, and transforming vacant, neglected, and underutilized land into a matrix of green infrastructure, just to name a few projects. From here, I will turn things over to my colleague Jennifer Dobkowski with the Climate and Fisheries Adaptation, or CAFA program, who will talk a bit about CAFA as well as NOAA's broader adaptation sciences program.
Thanks, Jeannie. Can you hear me okay?
Yep, we can.
Great, thank you. Hi, everyone. My name is Jen Dobkowski. I'm a program manager with the Adaptation Sciences Program, or ADSCI for short. As was mentioned before, the ADSCI program is a sister program of CAP and was established in 2021. There are 3 legacy programs that make up the ADSCI program: COCA, SARP, and IRAP, and they were melded together to create the current ADSCI program. The goal of the Adaptation Sciences program is to advance the knowledge, methods, and frameworks to move society beyond incremental adaptation to more widespread, connected, and transformative adaptation pathways. There are 2 key objectives of this program: to develop an understanding of key drivers and conditions that shape and enable adaptation, and identifying and promoting opportunities for the use of climate information to support preparedness and planned adaptation. Next slide, please. The ADSCI program prides itself on excelling at blending research, partnerships, and engagement. ADSCI supports work conducted both within the U.S. by co-leading the DOT partnership Climate Smart Transportation, and outside the United States by leveraging U.S. Department of State funding on projects such as the Island-Led Resilience 2030 and NOAA's Blue Carbon Inventory Project. AdSci also provides technical collaboration and capacity building by leveraging funding in areas such as fisheries, which I'll touch on in a minute, and coastal resilience. We shape and implement our program priorities by participating in various federal work groups and project-specific cross-agency collaborations. For example, in the nature-based solutions space, the FEMA guide Building Community Resilience with NBS and the Commission for Environmental Cooperation, which is the Canada-US-Mexico partnership effort, monitoring the efficacy of nature-based solutions, proposed methodology, and indicators. Nature-based solutions is a space that AdSci has invested in the past, and moving forward, we would like to focus more in this space and amplify our investments in the future by using our past work as a springboard. Next slide, please. Within the Adaptation Sciences portfolio, I am the program manager for the Climate and Fisheries Adaptation Program, which is also known as CAFA. CAFA is a partnership between the Climate Program Office and the NOAA Fisheries Office of Science and Technology. We fund external interdisciplinary research through a competitive peer-reviewed process. Our researchers are part of a national community of practice that promotes knowledge exchange and peer-to-peer learning. CAFA promotes technical collaboration and capacity building in areas that intersect with NOAA's mission. CAFA has evolved out of the COCA program, which you heard a little bit about earlier, the Coastal Ocean Climate Applications Program, which was focused on supporting interdisciplinary applied research designed to address the needs of decision makers dealing with pressing climate-related issues in coastal and marine environments. The COCA program had two focus areas. One, resilient coastal communities and ecosystems in a changing climate, and the second, climate impacts on fish, or COCA fish. In 2014, the COCA fish program was in response to some congressional interest in shifting fish stocks in the Northeast and the climate impacts related to that. In 2021, COCA fish was renamed the CAFA program to show our connections to the Adaptation Sciences program. The CAFA program advances understanding of fishing community adaptation and resilience in response to climate change, advances understanding of current and future climate-related impacts on fish and fish stocks to promote sustainable fisheries management, and develops tools and information that promote adaptation and resilience of the nation's fishing communities and fisheries in response to climate change. Next slide, please. Over the past 10 years, CAFA has invested approximately $20 million to support 32 projects in 5 regions. We've held 11 workshops, including a fishing community adaptation workshop in March of 2024, and we've brought together managers, members of fishing communities, researchers, and other stakeholders. We have expanded from our initial Northeast investment to include significant investments in 4 regions through 5 calls for proposals. Our funded projects assist in the development of climate-informed stock assessment advice, evaluating the vulnerability of fishing communities in response to climate impacts, and develop climate-informed ecosystem management strategy evaluation frameworks and advice, to name a few. And with that, I'm going to pass the mic back over to Jeannie to have her introduce our first speaker today.
Great. Thank you so much, Jen, for providing that background. All right, so now we can dig into the theme of today's episode. Nature-based solutions have been implemented for some time as a multifunctional, decentralized strategy for stormwater management. Locally, the benefits and co-benefits of these systems are well quantified. However, to address regional climate risks, NBS needs to be upscaled in non-trivial ways across urbanized landscapes. This upscaling poses several formidable physical, economic, and collaboration-related challenges. Addressing these challenges represents one of the front lines in advancing comprehensive resilience and sustainability planning. This webinar episode will feature how Franco Montalto with CAP's Urban Northeast team the Consortium for Climate Risk in the Urban Northeast, or CC-RUN, has leveraged funding from CAP and AdSci to advance science to support local action and broader scale adoption of NBS. Dr. Montalto is a civil engineer interested in the development of ecologically, economically, and socially sensible solutions to urban environmental problems, with a focus on water resources, urban sustainability, and climate change adaptation. His 30-plus years of experience have focused on nature-based solutions for ecologically restoring degraded ecosystems, treating wastewater and stormwater in constructed wetlands, and the implementation of green stormwater infrastructure systems. He is a professor at Drexel University, the president of eDesign Dynamics, an NYC-based consulting business. Montalto also serves as the co-chair of the 5th New York City Panel on Climate Change. Welcome, Franco, and thank you for being with us today. And as a reminder for participants, please use the question function to submit any questions you have for Franco. Please take it away.
Thank you. I'm just trying to share my screen. One moment. Okay, can you see me and hear me?
Yes, we can. Thank you.
Okay, great. Thanks so much for the invitation to speak today at this really important seminar series. I want to talk to you specifically about stormwater nature-based solutions. Obviously, there's lots of different types of nature-based solutions, but in the urban Northeast, where I'm one of the co-investigators on CC-RUN, we've been looking at the impacts of green stormwater infrastructure for a long time. CC-RUN has been around since 2010, and it's in its third phase of funding from the CAP program. And we're really grateful for that funding that gives us the opportunity to do this important work. So I want to acknowledge the work in here has many, many, many collaborators, many more than I could put on the screen, but I want to acknowledge Nicole Pearl, former PhD student Fatima Nasrallahi, and a research scientist, and other PhD student in my lab, Hasib Payab and Mobin Rahimi Gokanda. So, as we just heard, nature-based solutions this is a term that's used to refer to a wide range of strategies for reducing climate risks. And there's lots of related terms that, can be used as surrogates for nature-based solution, ecosystem-based adaptation, blue-green infrastructure, urban ecological infrastructure. This definition on the bottom is from IPCC, and it talks about this, the co-benefits of nature-based solutions, which is one of the reasons that that there's so much interest in them. You can solve multiple problems with the same approach. And they give examples of trees and vegetation and natural river systems and wetlands as some ways of doing that. In the water sector, nature-based solutions are used for a variety of purposes. So this definition here is from UNESCO World Water Development Report 2018, had a whole issue on nature-based solutions for water. And they talk about how nature-based solutions are being used to enhance water availability, improve water quality, sustain soil moisture in periods of drought, and also to reduce the risks associated with water-related disasters and climate change. So this sort of multifunctionality that is an attribute of general nature-based solutions sort of filters through into nature-based solutions for water. In the US, I would argue that the most common nature-based solutions in the water sector that we're seeing right now is green stormwater infrastructure, also sometimes or was previously called low impact development. In Europe, it's sometimes called through sustainable urban drainage systems. But these are a variety of strategies that in a decentralized manner try to detain, retain, filter, treat stormwater, which would otherwise cause water quality related problems within urban landscapes. And again, you see in this definition from the US EPA, the understanding that green stormwater infrastructure, although it's primarily implemented as a form of stormwater management, has these multiple benefits. And they're all different types of green stormwater infrastructure that have really become a billion-dollar industry in some cities. Many cities around the country have more than billion-dollar green infrastructure programs, many of which have been around now for more than a decade and approaching 2 decades. And here you see some of the types of green stormwater infrastructure that are out there. a couple of years ago, the Green Infrastructure Leadership Exchange did an investigation of what are the drivers. So this $1 billion investment in nature-based solutions is very unique. What's driving public investment in green infrastructure? And what they found is sort of follows my experience as well, that water quality regulatory requirements, so consent decrees on cities that have combined sewer overflows and permit requirements associated with stormwater dischargers are really, in 88% of these national respondents said that that was the main driver of investment. It was for improving water quality. However, the second most significant driver was this interest in the ability of green stormwater infrastructure to also provide a flood resilience benefit. And so I found this was a very significant sort of number one and number two set of motivations beyond this. But the problem, and this is what I want to talk about in this presentation, is that green stormwater infrastructure practices that are implemented as a form of water quality improvement are not explicitly designed to capture extreme events. And you might ask, well, why? Why is that? Because a number of reasons. One, going back to the 1970s and 1980s, there was a lot of research done around the country as part of the nationwide urban runoff program that determined that the bulk of the pollutants in stormwater are in the first flush. So this graphic over here on the right-hand side is on the x-axis is the cumulative amount of runoff, say from a storm, and on the y-axis is the cumulative amount of suspended solids, which are known to carry most of those pollutants. And what you can see is that more than 60% of the suspended solids are in the first 20% of the runoff. So that's one reason. There's this perspective that for water quality improvement, we really care about the initial first flush off of the landscape. And the second is this graphic over to the right that shows, for more of the temperate parts of the country, note the log scale on the vertical axis. This is for a bunch of National Weather Service gauges around the Northeast, shown in the upper right here. This is the percentage of all storms that are different depths, so 0 to 1 centimeters, 2 to 3, etc. And you see the log scale, right? 0 to 1 centimeter, nearly 100% of our storms are very small. And then you see 2 to 3 centimeters, that's only 10% of the storms are sort of an inch or so or greater. And then as you get further on, you see the percentage of storms are really small. So as a result, because both the recognition that most of the pollutants are in the first flush and the recognition that most of our storm events are small, most GSI practices are designed to retain, detain, or filter just the first 1 or 2 inches of runoff. And the consequence is that some of these extreme rainfall events that are becoming more common as a result of climate change will cause these GSI practices to overflow. And this is a graphic that we made as part of the New York City Panel on Climate Change Flooding report that came out last year. It shows here cumulative amounts of precipitation in New York City. That's on the vertical axis versus the time on the horizontal axis. And then those two dotted lines are the design standards for the rainfall depths that are mandated to be captured in stormwater systems that are installed in combined sewer districts and for houses in New York City. And what you see is that you could be completely in code and design facilities that capture that 1 to 2 inches of precipitation, but cumulatively the precipitation that's deposited on the landscape as a result of some of these extreme events, which include Irene, Sandy, Henri, Ida, a number of the big events that occurred over the last 10 years or so, would have exceeded and caused those systems to overflow. The other problem with extreme precipitation is that it's intense. And because it's intense, the rate at which the water is being applied to the land surface regularly exceeds the capacity of the land surface to infiltrate. So even if you don't have paved surfaces, even if you have a pervious landscape, there's the possibility that this intensity of the rainfall exceeds the infiltration capacity of the soil. And so here, this is some work that we did a number of years back. It looks, what I'm showing here is the infiltration capacity in centimeters per minute on the vertical axis. And then across the horizontal axis, you see all different types of surfaces that you find in cities, everything from parks to backyards to tree pits. And if I look at those storms that I showed in the previous graphic, this is the peak 1 minute intensity of all those storms. This was Ida at LaGuardia Airport. And what you see is that the rate at which the intensity of the rain exceeded the capacity of all those different surfaces, with the exception perhaps of some of these more synthetic rubberized safety materials or some porous concretes, which means that these quote unquote pervious surfaces would still be generating runoff under this extreme event. Nonetheless, EPA talks about the value of green infrastructure for mitigating flooding, especially under the context of climate change. And this is just from a state guidance document in Pennsylvania, talks about the role of green infrastructure in minimizing flooding. And that same study, the Green Infrastructure Leadership Exchange, also talks about the importance of better understanding the relationship or the role of green stormwater infrastructure perhaps in reducing flooding. And so that brings me as an introduction to the goals of this presentation. I want to focus on a particular watershed where we've been studying with the CAP funds to investigate whether the current levels of proposed water quality GSI could also reduce flooding. And then if not, determine how much GSI you would actually need to achieve that goal benefit. And then stress test that scenario with climate change scenarios and finally draw some conclusions about the topic of this presentation, the challenges and opportunities of upscaling GSI to reduce flooding. So the study area is in southeast Pennsylvania, just to the west of Philadelphia. You can see on the left-hand side, it's the Darby-Cobbs watershed. This is a 79 square mile, 205 square kilometer watershed with 31 different boroughs and townships. The two different creeks, the Darby Creek, the Cobbs Creek, that converge down in an environmental justice community in Philadelphia known as Eastwick, and that's shown to the right there. And as you can see, Eastwick, a large percentage of it is actually in the FEMA floodplain. So it's a low-lying area. And the entire watershed is flood prone. So this graphic on the left is some surveying that our CAP team did of individuals who live throughout the watershed. And we asked them questions like, do you believe that flood risks become better, worse, or do not change as the water flows through your municipality? And you see the vast majority said that as the water is moving downstream through this watershed, the flooding problem is getting worse. And this image on the right shows Tropical Storm Isaias, the last major storm to cause Eastwick to flood in up to a meter of water in some places. So a really significant set of flooding circumstances there. So our approach was using some of the NOAA COCA funds and CC Run Core funds to develop some modeling tools that could predict flooding in Eastwick as a function of its various drivers, so the precipitation, storms and surges, and their combined occurrence. And then using the COCA grant as well as the AdSci grant to interact with stakeholders to come up with a variety of adaptation scenarios, one of which is a nature-based solution, and then to use the modeling tools to simulate the effectiveness of these strategies to reduce flood risks now and in the future. So the project was kind of unique in its timing and sequencing. The COCA modeling started before 2021. AdSci project started in 2021. We convened a team of watershed partners. As I mentioned, 31 different municipalities. Actually, these municipalities don't regularly meet with one another. And so we created a voluntary watershed partners team. We also recruited, hired, and trained individuals who live in the watershed to assist us in the research. And they are what we call a watershed adaptation core. And so they were paid by Drexel University to help us with the work. And then we, over the course of many months, hosted a series of collaborative team meetings and technical meetings to discuss the work. And some of this work, which I'll talk about today, is about the hydrologic modeling of this green stormwater infrastructure. But there was a whole bunch of other stuff that we did. But I wanted to sort of introduce how we did the work. And the tools that we have developed are now being used and evaluated for various purposes, including flood planning in Eastwick. So for the modelers in the room, we used PC Swim, which is a proprietary version of EPA Swim, and we developed a 2D all pipes model of Eastwick. So what you see here is on the left, the larger watershed model, which was a distributed model, but not a 2D model because 79 square mile watershed in 2D would be prohibitively slow. But down in the most flood prone portion of the lower watershed, which is this environmental justice community, we had a 2D model. We worked with the city of Philadelphia and they provided us with their sewer pipes. So we had the ability to simulate every single catch basin and storm drain in that community. Again, for the modelers in the room, the 1D model connects to the 2D model. We had a 2D mesh, which had higher resolution within the creeks. It's probably more detailed than we want to go into right here, but it was a sophisticated modeling approach. Another unique attribute of this model, a lot of flood models are based on frequency events. So there's someone will analyze the stream flow at a USGS gauge and say, this is a 100-year flood, this is a 10-year flood. In our case, we use gauge-adjusted radar rainfall applied over the larger watershed, and we drove the model with that. And that's really significant because some of these extreme events that are becoming more common with climate change are spatially located. They're spatially concentrated, I mean. And so if you take one gauge and extrapolate that rain over a large land area, you may have some pretty significant deviations from what actually occurred. And here you can see Isaias, for example, was very spatially located in the upper watershed. To calibrate the model, we had, fortunately, 3 USGS streamflow gauges. And so for a variety of different events, we ran the model and simulated the stage at those locations. And here you can see Hurricane Irene, Hurricane Lee, Tropical Storm Isaias, several different locations. The model was quite good at replicating, after calibration, at replicating the creek stage fluctuations as a result of these extreme events. We also, with the COCA funds, interviewed or conducted surveys of residents in Eastwick, and you can see these dots of respondents who said that their house had flooded. And you can see also the overlay here of one of our simulations and the close representation of, or the close correlation between the surveyed responses. The U.S. Army Corps of Engineers also had high water marks and our flood simulations. And so this is what happened in Eastwick during Tropical Storm Isaias back in 2020. And you can see the area in blue is the area where the flooding is occurring. And so you can see a fairly significant event that had quite a big impact on the local community. So our goal here in this presentation is to investigate whether the green infrastructure that's being proposed or is already being implemented in the larger watershed could have reduced the flooding associated with Tropical Storm Isaias. So to do that, so in Pennsylvania, we have something called Act 167, which requires that counties prepare watershed stormwater management plans for each watershed, and they have to work with the local municipalities. And what we did is, since there are 31 different municipalities, a typical research team wouldn't have had the ability to go to each of these communities. But since we had our watershed adaptation corps, we asked those folks to go talk to the stormwater engineers and planners in each of these towns. And they generated a graphic like this. Now, you can't read this. It's really hard for us to read this, but this was our attempt to document, based on the plans that were underway in the different towns, how much green stormwater infrastructure was being proposed for compliance with this Act 167, with this water quality regulation, state water quality regulation. The thing that's most important here is that, at best, if you take all of the different approaches, bioswales, trees, porous pavements, basins, you take all of that and you upscale and you say, what's my best estimate of how much green infrastructure is going to go into this watershed? It comes out at best to treating about 12% of the impervious surfaces, which makes up about 5% of the total watershed area. So, we looked at that number initially and we said, is that big? Is that small? What would happen if we put that in the model? First thing we wanted to do, though, was to use the model to kind of do a little bit of a sensitivity. And the question we were asking was, obviously, will this amount of GSI reduce flooding in Eastwick? We were interested specifically in Tropical Storm Isaias. To simulate this, though, we needed to make some assumptions, right? There's all different types of green infrastructure that's being proposed. It's in a 79 square mile watershed. It's not possible to go in and put each type of green infrastructure in. So what we did was made some assumptions. We assumed that all of the green infrastructure could be represented as some version of a bioretention area, as you can see in this picture. This is a site that we have monitored in Queens for some time. And we assumed that on average, these practices would be about 300 square foot each. We also had to make some assumptions about how they would be integrated sort of on a block by block scale into the impervious sort of landscape around them. And that's a ratio that we call the hydraulic loading ratio. It tells you, if you have a 10% hydraulic loading ratio, or a hydraulic loading ratio of 10, it means that the impervious area that is tributary, that is directing runoff into the bioretention area, is 10 times the size, or in this case, 3,000 square feet, for example. So we allowed that to vary to consider different site conditions. And then we looked at a variety of different watershed, percentage of watershed treated, and percentage of the impervious area treated. So we wanted to consider a whole different set of conditions under which this green infrastructure might ultimately be built out, because this is all proposed. It has not yet been built. Again, to the modelers, swim-based tools have this great thing called the LID controls, where you're able to, actually it's got already built in the ability to put in different types of green infrastructure. You can then parameterize them based on their surface conditions, their soil conditions, their storage conditions, and then you can put them into the model at different ratios, and you can put in different numbers of replicates. So this makes this type of an analysis possible in PC Swim. So what we did with all of that is we ran hundreds of different model runs to look at different relationships of the peak stage at this point where you're seeing the arrow. This is where the Cobbs Creek overflows into Eastwick. And so if you look at those two dotted lines and you look at sort of a transect there, we drew them in those two figures, you can see that when that creek stage gets to 15 feet, it starts to overflow. When it reaches 15.6 feet, it starts to hit the first sort of houses along the banks. And so we developed this graphic. It's a little bit complex. Let me take you through it. On the horizontal axis is the Cobbs Creek peak stage, the peak water level at the Cobbs Creek, right? And you see the 15 and the 15.6. And you see that if you're between 14 and 15, there's no flood risk. If you're between 15 and 15.6, the creek overflows, but no building damage. And then above 15.6, you see gradually increasing flood risk to buildings, and that's why it's getting redder and redder. The vertical axis is the percent of the watershed, or the percent of the impervious area that's treated by green infrastructure in these hundreds of simulations that we did. And the different lines are different assumptions about the hydraulic loading ratio, about the percentage of the watershed treated, etc. And so there you could see that depending on how you implement green infrastructure, you're going to end up with peak stages in different points here, and they may or may not present a flood risk. If you look at what's already sort of being proposed, or what is being proposed by the municipalities, you're in this blue box somewhere. We don't know exactly where, because it depends how the green infrastructure plan rolls out, but you're somewhere in that black box, in that blue box, which means that this green infrastructure will be unable to reduce the flooding. You're going to still end up, at best, something like 7.2 feet of water at Cobbs Creek, which would still cause a catastrophic flood in Eastwick. So we already learned our lesson that what's already being proposed for water quality compliance is inadequate. We wanted to go further, though, and say, well, what if we took an ambitious GSI scenario that's in that region where the creek overflows, but there's no building damage? And that really gets us to something called 65, or at an HLR of 5, that's treating 65% of the impervious areas with green infrastructure. So if we run that with the model, this is what Isaias floods look like. And you'll remember before when I showed Isaias the last time, the creek overflowed, but here you can see it overflows a little bit, but not enough to kind of get over the hump and flood the vast majority of the community. So, and this graphic just shows it a different way. The orange areas are the difference between the no GSI and the with GSI, and the orange areas show areas where flooding was eliminated. And what's quite interesting about this is that not only is flooding eliminated inside of Eastwick, but it's also eliminated in some of the areas to the left, which is a different county. Those are some of the counties that are upstream of Eastwick. And so, this green approach has not just a benefit downstream, but also a distributed benefit. I mentioned that we wanted to then stress test the scenario. So what I'm showing here, I'm going to show 4 graphics. This is existing conditions with historical Isaias. That's the peak flood depths that I showed you before. In our climate, end of century is something like a 50% increase in precipitation with 4 feet of sea level rise. I should have mentioned that the Darby-Cobbs Creek is tidal because it's connected to the Delaware River, which is connected to the Atlantic Ocean. And so, as you would expect, going without the GSI, looking from top to bottom, climate change would increase flooding from an event like Isaias. But the GSI scenarios, under historical conditions, completely eliminate the flooding. But as the climate changes, that same ambitious level of GSI doesn't completely eliminate the flooding, but it certainly reduces it to what it would be under the status quo. So to answer our question, with sufficient penetration, GSI designed for water quality can reduce flooding now and in the future. But this begs a big question. So I said what's being proposed by the communities is inadequate. So this 65% of impervious area treated, what does it correspond to? What does it physically imply in the watershed? And it turns out, if you look at the the land use and the land cover, it means that all of the runoff from the rooftops, residential rooftops, would need to be treated, for example, in some kind of backyard rain garden. It means that all the street runoff would need to be treated, for example, in some kind of curbside bioswales. And it also means that all of the public fields and parking lots would need to retain their own stormwater. So there's a question here. That's a very different looking watershed from the typical suburban Americana watershed that we see there. And it's also much more GSI than is required for compliance with the water quality regs. So I bring this up because there's a lot of discussion about green infrastructure as a way of reducing flooding. I agree, and we've shown that green infrastructure can reduce flooding. But this brings us into an interesting territory in terms of what are we willing to visualize, or what kinds of landscapes are we willing to, or we desire to build in the future. They're going to have to be very different, and they're going to have to be integrated with nature-based solutions in a much more intensive way than what we're used to seeing around us. It also requires timely collaboration and synchronization of actions across multiple jurisdictions. And I bring this up because in the post-project follow-up, we're now working with the City of Philadelphia on flood planning, flood risk reduction in Eastwick. The green infrastructure approach that requires 31 different jurisdictions to kind of agree to upscale their nature-based solutions is somewhat off the table. It's not considered doable because of the difficulty in synchronizing so many different actions. So as part of our CAPRISA project, we actually did develop a tool for collaboration. I don't have time to talk about it right now, but it's a tool developed in Stella that has a special button for each one of the municipalities in the watershed, and you can click on each one of those towns, and then you can do things in those towns to change their impervious cover, change their the number of buildings, change the amount of green infrastructure. And what it does is shows you, and this is just some 2 screenshots. The upper one would be GSI in an upstream municipality, and you can see how in the graphic to the right there, the hazard drops over time as a result of this, the GSI that's being integrated into that municipality. But then if you look at a downstream municipality, also with green infrastructure being implemented, but nothing being implemented upstream of it, you see that you can put in as much green infrastructure as you want, but because you're downstream of a lot of impervious surfaces, that green infrastructure is not reducing your flood hazard. And so this is sort of one type of tool that I think can help at least to facilitate the types of conversations that you need over large watersheds to have this kind of synchronization. But there's a lot more work needed to promote that type of collaboration. So I'll say, just to conclude, the tripartite challenge that we have here is that upstream land uses cause and can be used to mitigate downstream flood risks. That we know, we've shown. But these topographic watersheds are subdivided into, from a physical standpoint, what are artificial areas, planning areas. These are municipal boundaries, and that creates some real challenges for collaboration and for watershed scale planning of nature-based solutions. The last piece I want to point out is that municipalities have a regulatory mandate to improve water quality, but currently we do not have a regulatory mandate to reduce flood risks and especially downstream flood risks. So there's a real challenge associated with this problem. I want to sort of conclude. My last slide is just some challenges to upscaling GSI, a form of stormwater nature-based solution that I think are worth keeping in mind. And one is the legal and regulatory barriers, right? So some goals are still not codified into law. There's nothing that says we need to do integrated watershed management. There's no rule that says that we must do flood protection of downstream communities. So without that mandate, we're sort of stuck with trying to shoehorn these co-benefits into programs that are mandated by law. For example, water quality improvement. Yet, it's rare to get co-benefits or to get credit for the co-benefits of a nature-based solution as part of those programs. So, for example, currently, if you're a municipality and you're putting in nature-based solutions for water quality improvement, one might think that that would make you eligible for some FEMA funding, for example, for flooding, or if a private property owner is putting in a nature-based solution, green stormwater infrastructure, that might reduce their flood insurance costs. And so those types of crediting are still rare. The second is expanding penetration in and across watersheds. So most of the green infrastructure that's going in is going in on the easy, relatively speaking, easy sites. So that's public sites and as protocols for development, so new development. But if you look at these land areas, especially in mature watersheds like the one I showed you here, a lot of the land was already developed. It's private land, it's small land. And so we need to spend a lot more time thinking about how to retrofit greening into private property, small private properties. I mentioned already the logistical hurdles and barriers to collaboration. We need to figure out how to work across political boundaries that exist in watersheds. And we also need to work across sectoral boundaries and to figure out how, since nature-based solutions are multifunctional by definition, how do you get credit from them to achieve multiple sets of goals and interests? And might that lead to some innovative cost-sharing opportunities? And in fact, that's barrier number 4 is studies demonstrating the cost effectiveness to support financing. So there's been a lot of work over the past 2 decades on looking at green infrastructure cost effectiveness, but it doesn't always reflect the type of partnerships that are necessary and the type of implementation that is necessary to also get this flood benefit. We need tools that help us to look at both monetizable and the non-monetizable co-benefits of different types of green infrastructure as alternatives to gray infrastructure. And then finally, and I think this is the most interesting one, we need to become better at visualizing the types of radically different watersheds we want to have in the future if we want these co-benefits to really be part of broader resilience planning. We've gotten very good at sort of plopping down green infrastructure systems here and there, standardized designs, doing them quickly, making them easy to permit. We need to get much better and much more creative at customization so that we can gradually create opportunities for greening a whole other dimension of the watershed. And that's a visualization, and that's a creativity, that's an urban planning goal that we need to set for ourselves. So with that, I think I will stop and look forward to the Q&A. I guess I will stop sharing my screen.
Yes, wonderful. Thank you so much, Franco, for sharing your fascinating work with us. We are now going to shift to our Q&A session, which our colleague Bhaskar with the Adaptation Sciences program will kindly moderate for us. Questions can still be submitted using the Q&A function. And yes, I will pass it off to Bhaskar.
Thank you, Jeannie. Really, really appreciate it. Franco, it was a wonderful, wonderful presentation. Thank you for all the information that you shared with us, with all the details and the pictures, and really, really appreciate your time on this one.
Thank you.
We have a couple of questions that are actually coming in as we're speaking. And I wanted to start off with this one. At what point in the process did you have a community engagement piece of it? And what did that look like? And did that have any impact on the project design or implementation at all?
Well, as I showed in that one slide, which was the timeline, we created a watershed partners team right away. we actually, I should back up with the COCA grant, which uh, started about a year before the ADSI grant. We had started engaging the community-based organizations in Eastwick. So the initial project was focusing on the sort of downstream end of this large watershed and what that community wanted to see. And so there were other options above and beyond green infrastructure. They were interested in a land swap, they were interested in a levee, they were interested in a variety of other options. But we quickly saw that the flooding problem in Eastwick, if you were addressing it in Eastwick, was sort of a band-aid on what was a larger wound that had to do with the functionality of the larger watershed. So that's when we wrote the ADSI proposal to engage the broader community, the broader watershed set of watershed communities. And then we created this watershed partners team, which included both the downstream and the upstream folks. And then we met with that sort of composite team in a series of collaborative team meetings that occurred every few months. So there were a number of things, like, for example, we didn't know going into this, and they didn't know what level of green infrastructure was actually already on the books as sort of possible in the watershed. So that was something that we gleaned from interacting with the various town engineers and stormwater managers and planners. So there were lots of places where the engagement helped us to sort of define the nature of the problem. I didn't know going into this whether, one way or the other, whether the green infrastructure that was proposed would or would not reduce the flood risk. So we had to find out what was being proposed, develop the model, then simulate it, and then formulate, conclusions about what options might be more viable. And so now, for the reasons that I mentioned, the discussion is focusing on stuff that can happen in Eastwick right now.
That's, thank you so much for that one. Now, based on that East Week example, here's another question that basically asks, how can we foster the cooperation needed to make progress on these kinds of collaborations? What are some things that you've learned in the East Week example that you think is transferable, applicable to other communities and collaborations?
Well, I think, one of the things that's been really interesting to think about is how to develop modeling tools. So we, in this particular project, we generated two different families of modeling tools, right? One was really technical hydrologic and hydraulic model that was designed in such a way that it could be used to simulate decentralized interventions in the watershed and their impacts downstream. That's already very different than a lot of the modeling that's done, that takes like a stream flow value that's sort of the downstream end of a large watershed, assumes that that's a given input, and then uses that to make, to study things that could happen further downstream. It doesn't enable you to look at things that happened upstream and the ramifications of those from actions upstream to downstream. So one sort of tool that I think is really helpful is watershed scale tools. Fortunately, there have been real improvements in the software capabilities and computational time required to do certain investigations now. So that, developing distributed watershed scale models to facilitate watershed scale problem solving is one thing. The second family of tools that we developed was, since not everyone has the ability to access those tools, were another set of tools that make the outputs from those tools accessible to a lay audience, or not necessarily a lay audience, but an audience of people who care a whole bunch about stormwater management, but just don't happen to have a consultant or a researcher team that can actually operate the models. And so in a different presentation, I could talk to you about that other modeling tool that we developed. I think there's a lot of work needed. I'm not 100% satisfied with the tool we developed because it's a complex problem, and you want to make an easily accessible tool, but you don't want to dumb down the problem so much that it's not useful. So I think there's a lot of interesting work needed there to make the watershed scale modeling of complexity accessible to a broad audience so that it can inform decision making.
Now, since you're talking about modeling, let me ask you this question. When you were actually as this work was progressing, did you have any particular GSI going in? Did you already have some ideas of what GSI technique you're going to use, and how did you calibrate the GSI into the model itself?
Well, so the GSI, as I mentioned, we had to make assumptions because when we looked at the pollutant prevention plans that the municipalities had developed, they were themselves quite ambiguous. They said we're going to do, we're going to put in 300 trees, we're going to put right-of-way bioswales, but as anyone who is on the call and is part of design processes know, sometimes you don't know the exact, until you actually go evaluate the site and implement and look at your budget and, look at site constraints, you don't really have explicit definition. So we had to that's why we ran all those different scenarios that I showed in that really complex spaghetti chart. So we knew generally that green infrastructure was being discussed, but we didn't know what types of green infrastructure and in what densities. So we then, used the tool to, look at various build out scenarios. So to answer the question about did we actually validate the tool against the green infrastructure that was proposed, well, that wasn't possible because this green infrastructure is still proposed. It hasn't been built. But I can tell you in previous work that I've done in green roofs, in bioretention areas, and porous pavements, that these swim-based LID controls, that's the tool. If the person who asked the question is a modeler, they can be. I have validated them against observations, post-construction monitoring observations that we conducted in actual green infrastructure systems. So the tools in general are reliable. The question, the uncertainty though, is like how will the green infrastructure get rolled out in the future? And it's difficult to say, but what I can say with certainty is that what is on the books in this particular watershed, and also in other watersheds that I've looked at, is way below what you would need to reduce flooding impacts. And that's, I think, that's the key take-home message here, is that if we want to take advantage of this co-benefit of green infrastructure, we need to upscale it. The amount that you need to reduce flooding is more than the amount that you need to improve water quality.
Now, as you refer to these models, I'm guessing some of them are models that you created, or some of them are standard. They're readily available. Are there any references or white paper or any other information that you can actually give the audience about these modeling? What you use, for modeling workflows. Just a question that one of the audience member actually asked. So if you could, if it's not now, maybe at a later date when you're answering these questions, I'd love to actually see if there are any references that you can actually share with us.
Sure, I can, as a follow-up, if you'd like, I can send you some papers and some links to the software that we use, and some papers that sort of show how the software can be used to replicate field conditions. In fact, I had some follow-up slides if there was more time to show you some of that work, but there isn't time. So but yeah, I can share some information as a follow-up.
Awesome. Thank you so much. Now, here's another question I thought, which I think, based on your experience and your team's experience, I think others would actually benefit from this. Now, you were talking about the balance of civil engineering, H&H modeling, landscape architecture, urban planning, in approaching large-scale GSI implementation project. Are there any groups underrepresented in your experience?
You're underrepresented in the actual implementation space.
Right, in the team, in your team, you have civil engineers, I'm guessing, right? You have H&H modeling, people with H&H modeling, landscape architect. Are there any other sectors that are missing for having a really good implementation project?
Well, I mean, we had social scientists, we had applied scientists, we had natural scientists, and I'm talking broadly in the COCA team and the AdSci team. We had Stevens Institute, we had University of Pennsylvania, we had Hunter College, we had Drexel. So we had a broad-based team. do I think anything was underrepresented in our team? No, except I do think that we did hire a law clinic to do some investigations on some of the adaptation options that we were talking about. And I do think it would have been nicer to have sort of policy and legal people more directly connected into this, as well as folks who kind of understand financing and cost sharing arrangements, or possible, innovative strategies for cost sharing and financing, because we can't achieve these goals through the same approaches that we use for water quality improvement.
Right. I do have one last question before we actually finish this. Now, with NBS increasingly looked as a potential option for some communities based on your work, what would you identify as some of the key research needs or gaps for implementation? One or two things that immediately comes to your mind.
For implementation of green infrastructure in large watersheds,
Mm-hmm.
we need
What are,
better platforms for collaboration that are based on better modeling of distributed interventions and simulating the effects of distributed interventions over large land areas for multiple stakeholders. That's, I would say, one thing that I would like to do a lot more of is, our model was sort of coarse in representing the upstream dynamics and much more detailed at the downstream end. But the same approaches that we're talking about that could have downstream benefits could also have benefits in intermediate points in the watershed. So, I think, would be interesting to have resources to get a little bit more explicit in some of the upstream dynamics and how those are represented in the model.
awesome. Franco, thank you so much for answering these questions very patiently. I'm going to switch it over to Jeannie. Jeannie, back to you.
All right. Thank you, Bhaskar, for facilitating that fantastic discussion. And thank you, Franco, for sharing your extremely important and insightful work. And thanks to everyone who joined us online today. Please mark your calendars for our 6th and final webinar in this series, taking place on Wednesday, February 19th, to learn about utilizing blue carbon as a nature-based solution to enhance management and carbon accounting of coastal ecosystems through international collaboration. Lastly, I wanted to give a big shout out to Aaliyah Mejias, who was CAP's former Sea Grant Knaus Science Policy Fellow, who recently started a new role with the DC Department of Transportation, who led the design of this webinar series and who was integral to making today happen. So thanks again for everyone for joining, and take care. Goodbye.